Hello students. Today I'll be explaining to you another example for DC motor analysis. This time we're going to be focusing on a separately excited DC motor. So as we have seen before in class, in order to analyze a DC motor question, we need three things. The first is the equivalent circuit of the correct DC motor type. So as you can see here, there's two types that we're going to focus on: separately excited DC motor, which has the circuit on the left, and the shunt DC motor, which is the equivalent circuit shown here in the middle. So we need these two equivalent circuits. Depending on the question, make sure you choose the correct DC motor type and make sure you memorize the correct equivalent circuit. Then we need the equations of the equivalent circuit. So for the separately excited DC motor, for the field winding, it is separate to the armature winding, so this is the equation, and the line current is equal to IA in the separately excited DC motor. For the shunt DC motor, the field winding is in parallel to the armature winding, so therefore they share the same voltage. So the difference between the shunt and the DC motor, when you want to calculate the field current, you have to use VT in the shunt DC motor. And in the shunt DC motor, the line current is equal to the sum of IA, which is the armature current, and field current IF. Now, for both types of DC motor, the armature circuit KVL is given by VT equals to EA plus IARA. And what is EA? EA is the induced voltage, is equal to K flux omega, where omega is the speed of the motor. And the induced torque is equal to K flux IA, where IA is the armature current. Now the flux is controlled by the field current. So as you can see here, the flux is proportional to the field current, and from the EA equation, when omega is fixed, then there's a relationship between EA and flux, and then there's a relationship between flux and IF. So the third thing we need to analyze the DC motor is a magnetization curve, which is a graph of EA against IF. So this is an example of a magnetization curve. On the x-axis is the field current, on the y-axis is the induced voltage, and the graph follows the shape of the BH curve, where as you increase the field current, EA will increase, but after a certain point there will be saturation in the machine, so when you increase the field current, EA will not increase as much. And this magnetization curve is always for one specific speed. Because why we need it at one specific speed? Because when omega naught is constant, EA will be proportional to flux, and flux will be proportional to IF, and that is how we get this graph. So what we're going to do next is we're going to do an example for the DC motor, and we'll look at calculating several things in the DC motor. So the example analysis for the separately excited DC motor will be broken up into 4 examples. In this first example, we'll look at calculating the no-load motor speed. You'll have a second video which will show the second example where you calculate the speed at a different condition, and then there'll be example 3 and example 4 in separate videos. So make sure you watch all 4 videos. So let's look at the first example, where in this first example, we're going to look at a DC motor with no armature reaction, and we're going to calculate the no-load speed. So the question says a 150 volt separately excited DC motor with compensating windings has an armature resistance RA of 0.2 ohms. The field winding of the motor has 1800 turns and a field resistance of 100 ohms, and an external resistance. Remember, in the DC motor you have an external resistance, and the purpose of this external resistance is so that you can change the field current. So the external resistance is connected to the field circuit, which has a variable value from 0 to 300 ohms. The field voltage is applied to the field winding, which is 180 volts. This is separately excited, so the field voltage is different to the armature voltage, and the magnetization curve of the separately excited DC motor taken at 1500 RPM has readings as shown in table 1 below. So instead of giving you a graph of the magnetization curve, we can also give you a table which is actually showing the same information. As you change the field current, how much is the EA? And this table is taken at the speed of 1500 RPM. So the question says, if the adjustable resistance is set at 200 ohms, calculate the no-load speed of the DC motor. Alright, so what we need to do first is to extract all the information, and you need the equivalent circuit. So don't forget, this is the equivalent circuit of the separately excited DC motor. The field winding has its own voltage Vf, and the armature winding has its own voltage Vt. So let's extract the information. So from the question, this 150 volts is the armature voltage. So therefore, in this question, VA is 150 volts. It's also VT. Okay, sometimes the armature voltage is written as VA, but most of the time in the textbook it's written as VT, which is terminal voltage, and it's 150 volts. It has an armature resistance of 0.2 ohms, so RA is 0.2 ohms. It has the field winding has 1800 turns, so the NF of the field winding has 1800 turns, and the field resistance is 100 ohms, so RF is 100 ohms. The adjustable resistance is variable from 0 to 300 ohms, and the field voltage is 180 volts, so VF is 180 volts. So the question asks, if R adjustable is if R adjustable is 200 ohms, what is the no load speed of the motor? So that's what we're going to find next. So I summarize all the information that we've extracted here. Table 1 is the magnetization curve at 1500 RPM, and the information that we have, VT is 150 volts, RA is 0.2 ohms. For the field winding, this is for the field winding, RF is 100 ohms, VF is 180 volts, and R adjustable is set at 200 ohms. Okay, so with R adjustable set at 200 ohms, the field current can be calculated. So IF is equal to VF. Look at the field current, field circuit, VF divided by the total resistance, RF plus R adjustable. So VF is 180, RF is 100 ohms, and R adjustable is 200 ohms. So that gives us 180 over 300. So therefore the IF is 0.6 amperes. Now, at no load, which is what we want to find, because the question is asking for the no load speed. At no load, what we must understand is there will be no induced torque. And we know that T induced is equal to K flux IA, and this will be equal to 0 at no load. So if there's no torque at no load, therefore at no load, IA at no load NL must equal to 0. Why? Because the induced torque must be 0. So now when you're looking at the armature circuit, we're going to find the KVL at the armature circuit, and the KVL at the armature circuit states that VT is equal to RA IA plus EA. So if we're talking at no load, then VT no load is equal to RA IA no load and EA at no load. Now, the VT is always 150 volts at all times. And we said just now the IA no load is equal to 0. So from this circuit equation, EA no load is equal to VT no load minus RA IA no load, and this current is 0. So therefore, at no load, EA no load is equal to VT no load, which is 150 volts. So this happens when there is no load in the armature circuit. The field current is 0.6 amperes because we have set the R adjustable at 200 ohms. So IF is 0.6 ampere. At no load, IA no load is equal to 0, giving us EA no load equal to 150 volts. Now the question is asking for the speed at no load. So we must find an equation that relates speed with EA. So to recap, what we got is when R adjustable is equal to 200 ohms, we found that IF is 0.6 amperes, and at no load, IA no load equal to 0, giving EA no load equal to 150 volts. Now, to find the speed at no load, or the no load speed, we know that EA is equal to K flux omega. So therefore, at no load, EA no load is equal to K flux omega no load, or omega no load is equal to EA no load divided by K flux. So omega no load is equal to EA no load divided by K flux, which is 150 divided by K flux, and we're going to call this equation 1. So what we need is to find this value of K flux. Now, in order to find K flux, we need to look at another condition. Of the motor. And in order to do this, we have to use one information which we haven't used that yet, which is table 1. Now, the field current, if the field current IF is equal to 0.6 amperes, according to table 1, when IF is equal to 0.6 amps, EA is equal to read the table, 102 volts, and this is at a speed n of 1500 rpm. So we're going to call this EA0, EA0 and N0. So according to our equation, EA is equal to K flux omega. So EA0 is equal to K flux omega 0. So from the table, when IF is 0.6 ampere, EA0 is 102 volts, which is equal to K flux omega 0. Now omega 0, we need to convert N0 into omega 0, which is N0 times 2 pi over 60. So 1500 times 2 pi over 60 gives us omega 0. So from here we are going to get K flux, which is 102 divided by 1500 times 2 pi over 60. And if we calculate this, K flux will come out to be 0.649. And we're going to call this equation 2. So now that we have a value for K flux, we can substitute this into equation 1. So substituting equation 2 into equation 1, we are going to be able to calculate the no load speed. So the no load speed omega NL is equal to 150 over K flux, and we know that K flux is 0.649. So therefore the no load speed is 231.12 radians per second. Remember, omega unit must be in radians per second. So the answer is the no load speed is 231.12 radians per second.